Hello, everyone. I'm Billy Younger, and I would like to take a few minutes to introduce you to basic trigonometry. I'm going to draw a couple rays, define an angle, and then create a bunch of triangles. Actually, just going to create three, but tell you how to create an infinity of triangles using those two rays, and they'll all be right triangles. And I'll explain what that is. And then I'm going to introduce the trig functions and explain to you how you can get them, and also maybe help you understand what they are, what they mean, and why there's six of them. So let's turn it back to our document cam. So if you want to make an angle, you just start by drawing two rays with a common starting point. So that's what I did here. I drew one here and I drew one here. This one's supposed to be horizontal. This one's at some diagonal. In fact, I made it a very specific angle that I'll tell you about later. And then I had a little snafu when I went to copy the sizes of these sides. I wrote them in the wrong place, so that's why those numbers are scratched out. The ones that are there now are actually the correct ones. So we have, with these two rays, I can now make a right triangle, and a right triangle is just any triangle with a single 90-degree angle. It can't have more than one because a 90-degree angle times 2 is 180, and the total sum of the angles inside of a triangle is 180, so you can't do that. So if you have a 90-degree angle in the triangle, you have a right triangle, and the 90-degree angle is indicated by this little box, which I like to tell my students to think of it as an arrow, because then it's an arrow and it also points towards the longest side, which has a special name. So the way I set this up, as it says over here, I basically made three perpendicular lines. I actually copied it to make it a little neater, and then I screwed it up again so it's still less neat. But anyways, if you take your time, draw it really well, and then be very precise with your drawings and measurements and stuff like that, and use very good instruments, you can get very good results. So what I've done here is I measured the sides of each of the three triangles, and of course there's three triangles, so you have three of each sides on each of the triangles. So all the black sides, their measurements are written in black, and they're called the adjacent, because the angle here, that's a Greek theta, Theta, that's a Greek letter theta, and that's an angle which you could use use a protractor to measure. And that angle I happen to have chose was pi over 6 radians, or 30 degrees. And the side that's actually touching the angle is called adjacent, because adjacent means next to. Now this side's also touching it, but remember this is a special name because the arrow points to it. It is the long side. And the longest side is called the hypotenuse, Hypotenuse. So the black lengths indicate the length of the adjacent sides of these three triangles. The green lengths represent the lengths of the opposite sides, and the red numbers represent the length of the hypotenuses. Now I also call these adjacent sides side A. The opposite side, I call it side B, as it shows here, and the red sides, I call it side C. So there's several different ways you can write that. Now, if you take the ratio of, say, this side to this side, so I divide 2.53 centimeters by 5.15 centimeters, and I do the same thing with 3.79 and 7.53, if I really did those very precisely, like if I did them on AutoCAD, for instance, I'd get exactly the right number. But if I did them very precisely, maybe with vernier calipers, and paid close attention to what part of the line I'm using, whether it's from outside edge to outside edge, or center of line to center of line, and what is the apex over here, that sort of thing. If I did all that very precisely and actually wore my glasses, I'd be able to get very precise measurements. And what you'd find out is consistently this side over this side is the same as this side over this side, and that's the same as this side over this side. And that's the same for any number of triangles I made on that particular two rays. Well, the problem is I used this scale, which is not very decent, very impressive. It's definitely not a vernier scale. I didn't wear my glasses, and the individual ink markings were a little bit problematic. So sometimes I might have accidentally measured to the center of the line as opposed to the edge, just out of inability to see. But if I was more precise about that, it would have come out even better. But you'll see, even as imprecise as I was, I get no more than 1.6% error, I think. So now, another thing is, if you do this side over this side, you get another number other than what we got for this side over this side. and this side is the adjacent. That's adjacent over hypotenuse. I get the same thing as if I did this over this, or this divided by this. So all of those are new ratio, but all of those should be roughly the same. In fact, it should be exactly the same if I do it properly. But like I said, I'm not that, I didn't do it that properly, so we're going to get a little bit of error. And you can also see that I could do this side over this side. So I could do opposite over adjacent, opposite over adjacent, opposite over adjacent. Now that gives me my first three fundamental trig functions. And because I labeled all these A and all these B and all these C, I'll show it to you in a couple of ways. So the first trig function I'm going to introduce you to is the sine function. And these words come from Arabic. This is actually, it's the same root as the word sinus. It means folds, if I remember correctly. But sine is the way you spell it, but we use the abbreviated SIN, and that's the sine, that's read the sine of theta, the angle theta. Now it's defined to be the ratio of the opposite over the hypotenuse. The opposite over the hypotenuse, the opposite over the hypotenuse, but that's also equal to B over C, or B over C, or B over C. So both of these can be construed as definitions for sine theta. In this case, it gave us 2.53 over 5.15, or it gave me 3.79 over 7.53, or it gave me 5.60 over 11.16. If you calculate those, you'll actually get that this one is 0.491, this one is 0.502, and this one, or 3, excuse me, on this one. And this one is 0.502. That gives me an average of 0.499. Okay, well, it turns out this is the sine of 30 degrees, which is also the sine of pi over 6 radians. Again, I will get to you later on what radians mean. Right now, I'm just giving it to you so you happen to remember them a little bit. But it turns out this is exactly equal to 0.5 with any number of zeros after it. So that's what the angle is supposed to be, or that's what the ratio is supposed to be. And this is what I got averaged at 3 sig figs at 3 decimal places, basically. And in fact, that gives me an error of only 0.2%. So only 0.2% error. That's pretty impressive. Now, the next one I'm going to do is adjacent over hypotenuse. And oddly enough, if you look at this angle over here, this angle, let's say we call it alpha, that angle and this angle are complementary angles. Complementary means that they add to give you 90 degrees, and you probably already knew that because the total triangle has to have 180. I took 90 right here, so the other two have to add to give you 90. So they chose the name of this next function very intentionally, and it's actually the adjacent over the hypotenuse. So it turns out that the cosine gives you, the cosine of an angle gives you the same thing as the sine of the complement to that angle. So this cosine of theta that I'm going to write now, of theta, we're going to abbreviate that cos theta. That gives you the sine of the co-angle to theta. So if I did, instead of cosine of theta, if I did cosine of alpha, I would actually get the exact same 0.5 value. And you can see why that is, because the adjacent over hypotenuse for alpha is this, which is what we normally call opposite over that one. So that's why that's called the cosine as opposed to some other random name. Well, this one's defined to be adjacent over hypotenuse, which is also equal to, of course, to A over C. And when I measured these and did their ratio, I found out the values were 4.36 or 4.36 over 5.15. This is a 4. I need to make sure y'all can see that. This is a 6.45 over 7.53. And then finally a 9.52 over 11.16. Now, when I calculated these, they turned out to have given me 0.847. I was actually sort of disappointed in these. 0.857 and then 0.853. I happen to know that the cosine of 30 degrees, which is also the cosine of pi, I should put it equals there, of pi over 6, I happen to know that 0.866, but in fact, my average gave me 0.852. That is actually, in fact, a 1.6% error, so that was the worst one. But still, it's only 1.6% error. It should be about 0.866. It turns out to be the square root of 3 divided by 2. So that's what it actually is. So you can see the cosine of 30, which is cosine of pi over 6, is 0.866, even though I was really trying to fit stuff in there and didn't actually fit the equal symbols in there too well. So let me introduce you to the third fundamental trig function, and this one's called tangent. Tangent theta, which we just write as tan theta, which is defined to be opposite over hypotenuse, which is also equal to C, or excuse me, is also equal to B over C. Okay. When I did that, I actually got the following numbers: 2.53 over 4.36. You might ask, where are these units going? Well, when you divide a centimeter by a centimeter, you lose the units. You end up getting a dimensionless quantity, and a tangent's supposed to spit out a dimensionless quantity. I got 3.79 over 6.45, and I got 5.60 over 9.52. If you take time to use your calculator and calculate these, you'll get 0.580, 0.580, and 0.588. You can see they're really close to each other, which is important. That's the fundamental idea behind that, that no matter how big the triangle is, the ratio of the sides should always be roughly the same. And we're getting pretty close to that. This is kind of a way off from those two, but it's still, like I said, I'm using crappy rulers and stuff like that. Well, that gives me an average of 0.583. And it turns out that the tangent of 30 degrees, which equals the tangent of pi over 3, should actually be 0.577. That means this is an error of no more than 1.0%. So really, that's not too bad. Now, that's the first three fundamental ones. Now, and I've told you why you've got sine versus cosine. The co gives you the sine of the complementary angle, and the sine gives you the cosine of its complementary angle. But now the other trig functions have different names. So let me introduce you to those. I'm not going to do the times of the ratios. You can feel free to do that yourself. And I highly recommend you do this one time with just some angle. I use 30 degrees. That's a nice one. Another one's 45. That one shows you some ambiguities, though, because when you do a 45-degree angle, both of these sides are equal. And you might try 60 degrees. All three of those are really good. Now, in addition to sine, cosine, and tangent, we have cosecant. We have cosecant, which is spelled that way. Cosecant of theta, which is abbreviated cosecant, CSC, of theta. Now, that is, in fact, the inverse of the sine. So that's 1 over the sine of theta. So it's not the inverse function. It is the reciprocal, if you will, of the sine function. So the sine function was opposite over hypotenuse. So this one must be hypotenuse over opposite, or, in fact, C over B. Okay. The next one is secant, which this is cosecant, the next one's secant. So you can tell that these two are going to be co-angles of each other. So secant of theta, which is just written secant theta is in fact the the reciprocal of cosine theta. Cosine theta was adjacent over hypotenuse, so this must be hypotenuse over adjacent. And that, of course, must be C over A. And then finally, we have a co-angle to the tangent, and that's the cotangent. I don't know why I use a capital in the beginning of the first letters for all of them but tangent, but I always have. So this is going to be COT of theta, and that is, of course, 1 over the tangent of theta, and therefore it's opposite, or excuse me, it's adjacent over opposite, because the tangent was opposite over adjacent. And of course, it also equals A over B. So now you can see why we have 6 trig functions, and we've even learned what the co means on each of them. And finally, we've learned a way to actually figure out an individual trig function. Like if I want to know the sine of an angle, I just use a protractor and I make that angle with 2 rays separated by that angle and a common vertex, and then just draw a right triangle somewhere along that. In other words, make a line that's perpendicular to one of the rays, and then measure the opposite over adjacent if I want the tangent, the opposite over hypotenuse if I want the sine, or the adjacent over hypotenuse if I want the cosine. So that's a way you can actually get your trig functions anytime you want. There's other ways that are done much more precisely, so you can get as many decimal places as you want. That's not really that relevant to us, but the main thing is now you know the trig functions. Now, there's 2 sayings that people use to remember these first 3 trig functions. Mine is some old horse. Now check out the bad grammar here. Came a hopping through our alley. And I don't know why I switch back and forth between caps and lowercase letters. The important thing is some old horse, sine opposite over hypotenuse, came a hopping, cosine adjacent over hypotenuse, through our alley, tangent opposite over adjacent. Whoa, I'm glad I was just going over that because I had written this wrong, and I don't know why I did. I wrote it wrong there, and I wrote it wrong there. It's opposite over adjacent, opposite over adjacent. Hopefully I didn't make that mistake in my words. I just wrote it that way. I think I was looking at what was above. So your trig functions are opposite over hypotenuse, some old horse, came hopping through our alley, opposite over adjacent. And then you just remember that the cosine is the GOAT. It's the greatest of all time. Why? Because it has the secant as 1 over itself, whereas the other one has a cosecant, so that's not as impressive. So I just use that, the cosine is the GOAT. It's the greatest of all time. Another thing that most people use instead of this hickey statement that I like to make up is so. They spell it so, ka, toa. So, ka, toa. This is an H, not an M, because we don't have any M spelled sides. So, ka, toa. That's another way you can use, another mnemonic you can use to remember these first trig functions. And just remember that the cosine is the GOAT. So hopefully that'll help you keep straight that the cosine is the one that has is 1 over the secant, and the secant, of course, is 1 over cosine. So that just tells you, okay, well, the one I have left, I know it's not tangent because that's other function is cotangent, but in this case, it actually happens to be cosecant. Once you look at that, you can also see some neat little things. Like it turns out that if you take cosine, I don't want to use blue, I want to use this. If I take cosine theta and divide it by the sine of theta, well, cosine theta is opposite adjacent over hypotenuse, and sine theta is opposite over hypotenuse, like that. So you see the hypotenuses cancel out, and I get adjacent over opposite, which is in fact cotangent theta. So I get cotangent theta. I don't know why I went rid of S there, that's bad. Cotangent theta. Now, if you also take sine theta and divide it by cosine theta, then you get opposite over hypotenuse divided by adjacent over hypotenuse. And remember, when you divide a fraction by the fraction, you multiply by the reciprocal of the denominator, and that completes the multiplication. So I'm doing opposite over hypotenuse, because that's the numerator of the fraction, times the reciprocal of this, that's hypotenuse over adjacent. Reciprocal, remember, just means flip it over. So the hypotenuses cancel out, and I get opposite over adjacent, which is tangent theta. So we now have two identities to get rolling on. Sine over cosine equals tangent. Cosine over sine equals cotangent. And you probably can find another one if you divide a couple other angles. So I'll leave that to you. And that's it. I hope this video helped you understand a little bit about trig functions. Remember, this part was a boo-boo. I always make the document that I create, I make that available on my Google Doc. So if you want it, you just email me at Billy, B-I-L-L-Y, at physics, P-H-Y-S-I-C-S, solutions, SOLUTIONS.com. I capitalize the P in physics and the first S in solutions. But it really doesn't matter. You just email me at billy@physicssolutions.com and tell me what you want, and I can send you this. I'll send you a link to my Google Docs. I hope that helps. I hope you all enjoy math and have a good day. Bye-bye.